distribution of a population. Okay, so I'm going to say that this population has a mean of 100 and a standard deviation of 20. Okay, notice that I use mu and sigma to represent the mean and the standard deviation, right? And I did that because I'm talking about a population, I'm not talking about a sample. So when I use these Greek letters, mu for mean, sigma for standard deviation, I'm talking about the true mean and standard deviation of the entire population. So this could be everybody in the United States. It could be all males between 20 and 40 in New York State. It could be all people with diabetes in nursing homes. It could be a New York City nursing home population of females between 65 and 85. So you can define what the population is, but whatever you define the population as, this represents everybody in that population, the mean and the standard deviation, the center and the spread of that population. Okay, so I can, if it's a normally distributed population, what is normally distributed again? Normally distributed means that the variability is really a variability in terms of like who has a higher score or lower score is almost completely due to chance. Remember that binomial, that Galton machine that we were looking at with the balls dropping down and half of them would go one way and half would go the other way? Well, we know that one of the properties of a normal distribution is that the most of the values, that individual values in that population are going to be closer to the mean rather than further away. As you get further and further away from the mean, you find fewer and fewer people that have that value. Let's say that this represents blood pressure, for instance, right? So if the mean blood pressure of the population is 100, our expectations, if it's a normal distribution, is that half the population is going to be under 100, half the population is going to be over 100 because the average is 100. The median, middle value, the 50th percentile, is the same as the mean. You know, that's not always true. Sometimes you have a non-normal distribution, which is skewed, and the mean and the median are not the same. And we say to ourselves, okay, that seems interesting enough, right? So how do I go from here to what this population looks like in the way that it's distributed? Well, more of these people are going to be closer to the mean, fewer and fewer are going to be further away from the mean. And we know we talked about there's a formula that represents the density, the probability density for this population, and winds up looking something like this. It's typically, I didn't draw it very smoothly, but it's typically a bell-shaped curve, which is symmetrical. The left side looks identical to the right side. Left side for the mean, right side for the mean look identical. They flip over, they're the same shape. And the middle is at 100, is at the mean. And we know there's certain properties that this normal distribution has that we can apply to it. You guys remember the empirical rule, right? And the empirical rule told us that 95% of the people in a population that's normally distributed, 95% of the people in this population are going to be between 2 standard deviations below the mean to 2 standard deviations above the mean. Okay, so in this case, that would represent 20 times 2 is 40. That would represent 60 to 140, right? 95% of the people are going to have a blood pressure between 60 and 140. I'm making these numbers up. Obviously, you're not going to get very many people with that low blood pressure, or even lower, unless they're not living or something like that. So at any rate, and I know also that, I know a little bit more. I know that 1 standard deviation below the mean, which would be 80, and 1 standard deviation above the mean, which would be 120, that 68% of the population is between those 2 values. So just knowing the mean and the standard deviation of a normally distributed population tells us an enormous amount about how that population is distributed. So you can look at this at 2 ways. You can look at this range as represent 95% of the people in this population. You could also look at this as a probability. In other words, if I were to randomly select one person from this population at random, there's a 95% chance that that person would be between 60 and 140. Makes sense, right? Because 95% of the people are in that range. If I just pick one person, 95% of the time, I'm going to find that that person is between those two numbers. Now, 5% of the time, they're not going to be between those two numbers, right? Between 60 and 140. 5% of the time, they're going to be either less or more. And since this is symmetrical, it may not look like it, but since it's symmetrical, you know that that means that 2.5% of the people are going to have blood pressure over 140, and 2.5% are going to have a blood pressure under 60, right? That's what our normal distribution does for us. Now, if there's any other value here, for instance, if I ask you, what's the probability that I would select an individual from this population that has a blood pressure equal to, that has a blood pressure which is less than, let's say, 70. How would I figure that out? Well, less than 70, let's see, where would that be? That would be over here. It'd be between 80 and 60. It's not a whole number for a number of standard deviations for my empirical rule. So I can't really apply the empirical rule. I do know that, yeah, I can get a rough idea. Well, it's outside of the 68%, and this is 34%, and this is 34% because they're symmetrical about the mean. And then this part over here, I can kind of guess where it is, but I don't know exactly, right? Because I can't use the empirical rule to figure this out more accurately. Empirical rule is an estimate anyway. Okay, so if I want to figure out what the area is, what the probability of having someone who has a blood pressure less than 70, or what percentage of population less than 70, I need to find this area in here. Okay, and how am I going to do that? Well, what I need to do that is I need to know the number of standard deviations below the mean that this value 70 represents, right? So in other words, I need to know number of standard deviations, which we also call the z-score. Z-score is just another way of saying the number of standard deviations away from the mean. If it's a negative number, it's below the mean. If it's a positive number, it's above the mean. So 120 would have a z-score of +1. 140 would have a z-score of +2. Okay, so in this case, our z-score is going to be the number of standard deviations below the mean. And I can calculate that by just taking the value I'm interested in minus the mean over the standard deviation. Again, I'm working with the population again. So z is equal to the value I'm interested in, which is 70, minus 100, the mean, over the standard deviation, which is 20. So that's 30 over 20, or 1.5. Okay, so I accept that. Remember, I got to keep my signs in place here. 70 minus 100 is minus 30, so it's minus 1.5. That makes sense because it's to the left of the mean. So what do I do now? Well, now I have to figure out what that area is. What's the probability I would pick someone out that's in that has that value. Okay, so I'm going to have to look for that. Let me just, in the meantime here, turn off these notifications so that, there we go. We don't keep popping up while we're trying to pay attention to other stuff. Okay, good. So I need to get to a z table in order to figure that out. And I'm going to search for one. You have it on Blackboard, I think. If I don't have it in this week's session, I'm sure it's there also. I'm going to use one from another textbook called Agresti. It looks exactly like the one in your textbook. So z table. This is the one that I've been uploading to Blackboard. You could use the one in the textbook. It's almost identical to this. Okay, and here it is. It's actually 2 pages. The one in the textbook and this one happen to be 2 pages. They have all the negative z-scores, right? 0 and negative to negative 3.4, and positive z-scores 0 to plus 3.4. And that represents the z-values above the mean and the z-values below the mean. Now notice when we're looking below the mean, it's always to the left of the mean. So the area that this returns or gives us is that for any z-score, it gives us this shaded area, the area to the left. In our case, that's what we're looking for. So in our case, we're looking for negative 1.5. So negative 1.5, the next digit, if you were going to use it, is going to be in the columns to the right of this. So negative 1.50, which is what we're after, is this area right here, 6.68%, or 0.0668 as a proportion. So negative 1.51 would be this, 2, 3, 4. So this each column represents the next digit. Okay, so if I had a positive z-score, well, then let's say a positive 1.5. Positive 1.5, the area to the right of that would be 0.9332, 93%. Why is that? Because it's all the way over here. And this table always gives you the area from your z-score to the left, the area below that value, right? So in our case, we're happy with our z-score, which turned out to be 0.0668. So I'm going to go back to our drawing. So this area is 0.0668, right? A little less than 7%. Okay, on an exam, a homework, I'll probably tell you whether to put it in as a proportion or a percentage, 6.68%. Okay, and you can make reasonable judgments about rounding and stuff like that, but to tell you the truth, you really don't even have to round. If you want to avoid rounding errors, you can just use the actual answer that you get. Now, you particularly don't want to round if you're going to do, if the calculation that you made is just the first part of a calculation. In other words, if we're then going to use this as some other calculation, so if we were to round this to 0.07 and whatever we had to do required you to square that, well, that automatically magnifies the error that you make in rounding it off, right? So you don't want to round it. If you round it all, you don't want to do it until you're done with all of your calculations. So the area here would be 0.0068. Well, let's see, what about if I asked you, what's the probability of a person having a blood pressure that's less than, let's go on the other side here to here and call it less than 130. Well, this one, 30, let's see, 30 minus 100 over 20, this one's a positive 1.5, right? And literally, I just did that, didn't I? Okay, that's going to be right over here. That's going to be a plus 1.5 z-score. So we're looking here at our z table. Okay, and we're going to go to our positive numbers this time because we know this number is going to be, since it's on the right side of the mean, we know the area to the left of this number is going to be more than 50%. So it turns out to be 1.50, 0.9332. Okay, that turns out the area from here down, okay, and I'm going to cross hatch it this way. The area from there down turns out to be 0.9362. I'm getting a little spazzy there on my drawing hand here. 0.9362. Okay, about 90, almost 94%. Okay, so if I asked you what's the probability that a person has a blood pressure which is greater than 130, well, it would just be that 90 to the area over here, which is 100% or 1.000 minus 0.9362. Okay, whatever that comes out to 8,396.0638. Right, pretty close to what we got there. Matter of fact, it should be exactly the same. It's exactly the same as what we got. Nope. Well, I'm not going to worry about that for right now. So at any rate, the area above this, I could get by subtracting it from 1. Okay. What if I asked you what's the probability of the blood pressure being greater than greater than 70 and less than 130. That would be the area between these two values, right? It would be this area in here between these two values. And since we know from this point down represents 0.9362, and from this point down represents 0.0668, the area between them, if I just take this larger area and subtract this, I'm left with the area I'm interested in, which turns out to be, let's see if I can do this quickly, a 4. Count 1, this is going to be 9, count 2, 2, 12, 6.0, I'm sorry, 0.8694, I think. Okay, I'm not sure I got that right. I'm working real fast, as fast as I can. Okay, so that's going to be the difference between these two. Okay, so I'm going to pause for a second. Are you guys okay with that? Make sense to you? Yeah, I'm talking to you. I'm facing you. I'm talking. I know I'm staring into the screen most of the time, but when I look up and I look at you, you comfortable with that? How about down there at the other end? Okay, we're pretty good with that, right? Okay, good. That's an important first step on what we're going to do now. How about you guys online? How do you guys feel about it? Okay, this is kind of little. This is kind of a review of the last thing we did. It's been 2 weeks since we did it, so I wanted to make sure that we were all on the same page with it. Okay, good. I'm glad to hear it. At least I got some positive feedback online. Okay, so now I'm gonna take the next step here. And that next step is that I'm gonna bring up this distribution we just talked about again. I said the mean is equal to 100 and the standard deviation is equal to 20. Again, I'm talking about a population because I'm using Greek letters. In other words, parameters. We call those parameters. Parameters. Okay. So when I'm talking about a sample, I use X bar and standard deviation, right? That, because I want to distinguish between the mean I get from a sample and if I know the mean of the population, the real mean of the population. Okay. The problem here is that we never know this, right? The only way to know the mean and the standard deviation of a population is to measure everybody in the population. But ultimately, that's the only thing we're really interested in. So it's a quandary. The only thing we know about a population is when we take a sample from it of a certain size, we know the mean that we got, we know the standard deviation that we got for that sample, and we know the sample size that we use. We don't know the population mean, and we don't know the population standard deviation. We don't even really care about the sample mean and standard deviation, right? That's not what we're interested in. We're interested in the population, not our one sample that we took. The problem is that since we will never know the mean and the standard deviation of the population, the sample is the results of the sample is the only clue that we have to what the mean of the population and the standard deviation of the population is. So the idea here is that if I take my population, mean is 100, standard deviation is equal to 20. If I take my population and I randomly sample that population, I'm going to say I take 100 people. My sample size is equal to 100. And I randomly sample that population, right? A sample size of 100, pretty big sample. If I calculate the average for that sample of 100 people, and it comes out to it may not we know we secretly know the population mean is 100, but it would be very rare, very unusual for us to get lucky and get exactly the population mean. Maybe we'll get 102, maybe we'll get 98, maybe we'll get 99. I'm going to say, for argument's sake, our sample mean was 96, right? We're pretty close to 100. We're not exactly 100. So I took a sample size of 100. We also could use this, and our theory here is if I take a nice size sample, my sample mean approximates my population mean. It's not equal, so I didn't use an equal sign. I used an approximation sign. It approximates it. The problem here is that by just taking a sample of size 100 and finding that the average for those 100 people, the average blood pressure is 96, you might ask me, well, okay, Tony, that sounds great. How close are we to the actual mean? And you want to know something? I have no way for me to tell you. I can't tell you how close we are to the actual mean, right? It's not obvious from what the sample mean is. So we need a way to describe how accurately we know the mean or how close we can get to what the actual mean actually is. In other words, maybe instead of just saying it's 96, maybe I can say, well, our sample came up 96, but based on the variability, the standard deviation of our sample or whatever that we know about this whole thing, maybe based on how variable these numbers are, I could tell you, well, I don't, our sample came up 96. I don't really know what the mean is, but I do know that the mean is likely to be between, I'm going to say 90 and 110. 104, let's say. Okay, we're a little bit closer to 90 than that. Okay, so it's somewhere between these two numbers with a certain level of certainty. That would be a good substitute for me having to predict how close I am, since I can't anyway, to the actual mean, because I don't know what the actual mean is. Maybe it's another way for me to look at this. And in fact, that's what we're going to be doing. That's what this is all about. That's what we ended the last class with. The idea that, and I'm going to start again on a fresh piece of paper. The idea that if I know a population, right? If I know a population mean and a population standard deviation, mu equals 100, sigma equals 20. If I know that about a population, 100, right? If I know that if I take samples of a certain size from this population, I'm going to say size 100. If I take 100 people from this population and find the average for my sample of size 100, and X bar comes out to be, let's say 96. I'm going to call it X bar 1. I do it again. This time I get an X bar of 102. I do it again, another 100 people. This time I get an X bar of 99. I know that if I do this 100,000, 1,000 times, 100,000 times, an infinite number of times, I know that these numbers are going to approximate, right, all of these averages. If I take the average of all of these sample averages, sample mean averages, that's going to equal my population mean. So the average of all of these repeated samples is going to be my population mean, because half the time I'll get a number by randomly sampling, get a number below and the number above, because it's a normal distribution. It's symmetrical. So now the next thing I know is that these numbers are not going to be as widely distributed as the population itself. Remember, the population itself was 95% of the people were between 60 and 140, right? Because that our standard deviation was 20, right? That was 95% of the people. Well, when we take a sample from this population, I wouldn't expect to take a random sample of 100 people and get 59. In order for that to happen, all 100 people that are randomly selected would have to be way down here. The chances of that are like astronomically small. So these numbers are closer together. And in fact, as in last class, we discovered there's a relationship between the sample size and the distribution of these sample means. And that relationship is that the standard deviation of the sample means, is equal to the standard deviation of the population, sigma, over the square root of the sample size. In this case, that's 20 over the square root of 100, which is equal to 20 over 10, which is equal to 2. Oh, so now if I take repeated samples, if I take an infinite number of samples, my mean is going to be 100 for these sample means, and my 95% of the time it's going to be between 96 and 104. Okay, my sample mean, right? Occasionally I'll get a value smaller, occasionally I'll get a value larger, right? In fact, 5% of the time I'll get a value either smaller or larger, because it's two standard deviations that I just did here, right? But most of the time I'll find them in between here. Okay, so if we know the population standard deviation, we know this perfectly. We can predict what a sample is going to look like in terms of how much it varies from the population. Well, again, we got a problem here. We don't know what the actual mean is, right? So I'm going to take the next step here. And the next step is I'm going to make believe, rather than talking about taking 1 million samples and coming up with a new distribution, I'm going to take one sample. I'm going to take one sample. I'm going to say X bar is equal to 96. Just the same thing that we were just looking at before, right? And I'm going to say our sample size is equal to 100, right? And mu is unknown. We don't know what mu is, right? Maybe really secretly we know it, right? Sigma, now to start off with, for today only, right? For today only, I'm going to say, I know the population standard deviation, right? You want to know something? Even though in most cases we don't know the population standard deviation, there are cases sometimes where we kind of can guess at it. Because, for instance, let's say you're doing a study where you're sampling 100 people in a population, but somebody last year did a study that sampled 5,000 people in that same population, and you just want to check if something changed this year. So you're only working with a sample of size 100, but last year they were working with a sample of size 5,000. That's such a big sample. You might say the standard deviation for that 5,000 person sample last year is so close, going to be so close to the population standard deviation. I'm going to make believe that I know the population standard deviation, that I know what sigma is. Even if you don't want to believe that, even if you don't want to accept that, just let's make believe that we know what sigma is. The reason why I want to do that is because I want to be able to use the formula that we just used. Okay, so our mean that we found was 96, X bar, right? That's the mean that we found in our sample of 100 people. So now, that's a sample of 100 people. How much different would it be if I took more samples? How much would these samples vary from the mean in terms of lower values or higher values from what I got? And for the moment, I'm going to assume that the mean really is 96, right? I'm not going to bank on it yet, but I'm going to say, let's say for an argument's sake that the mean is 96. I'm going to say to myself, well, I know 95% of the values would be to the left of that 2 standard deviations and to the right of that 2 standard deviations. But we're talking about the values for samples of size 100. So I'm going to add and subtract. 2 standard deviations. Two standard deviations from what X bar is. But those standard deviations, they're standard deviations of the means, right? Repeated samples of size 100. Remember what we said that was? That standard deviation of the means. We said that that's equal to sigma over the square root of n. So that's equal to, I'm not going to do it again, it's the same numbers. That was equal to 2, right? It was equal to 20 divided by the square root of 110, so it's equal to 2. Okay, so X bar plus or minus 2 times the standard deviation mean. When I say standard deviation, I could be talking about the standard deviation in a sample. I could be talking about sigma, the standard deviation in the population. But here, I'm talking about the standard deviation. If I took samples of size 1 over and over again, I made a new distribution from all the different means I calculated from each of those samples of size 100. I'm going to give that standard deviation a special name. I'm going to call it the standard error. It's a standard deviation. I'm just going to call it standard error, just to distinguish it from everything else. So this is the standard error, which is really the standard deviation of the means. Okay, so I'm going to say 96 plus or minus 2 times the standard deviation, standard error, standard deviation means. So it's plus or minus 4. So that is a range of 92 to 100. Well, what does this tell me? If 96 were the mean, the true population mean, and I took samples of size 100, the chances are 95% that I would get a value for that sample of 100 that's between 92 and 100. Well, wait a second. What if I use this backwards? My sample in 96, I could argue there's a 95% chance that that's within the same range of the actual population. I kind of turned that around on its head. So, in fact, by doing this, my range here is a confidence interval, right? In other words, I have 95% confidence. Why 95%? Because I took 2 standard deviations. 95% confidence that the true population mean, mu, which I'll never know, is between these 2 numbers. Think of the power that gives me now. Now I take a sample of size 100, I get a mean of 96, and I report my mean, our sample mean is equal to 96. However, our 95% confidence interval is 92 to 100. Not only can I tell you that my sample mean was 96, but now I'm 95% sure that the real population mean is between these 2 numbers. So rather than try and predict how close I am to the mean with 96, I'm giving you a range with a level of confidence, but I'm telling you that I have a certain level of confidence that I can predict accurately that it's between a couple of numbers. That means that you're 100%, you're going to capture the mean 100% of the time? No, 5% of the time it could be outside of this range. But at least we can say we're 95% certain. Okay, so now I'm going to ask you a quick question. Yes, yes? You beat me to it. I was going to ask a question, you beat me to the question. Yes?
What do you mean with the 4?
We got the 4 from 2 times the standard error. That's 2 standard deviations, right? Two standard deviations times the standard error, which was equal to 2 for the sample means, right? You get that from sigma over the square root of n, okay? And as we practice this, it'll become clearer. You'll know where to get those numbers. Matter of fact, it's interesting you got the 2 there because the 2 is a little bit of a white lie, right? That 2 is a bit of a white lie because remember the empirical rule? The empirical rule said that 95% of the results are between 2 standard deviations to the left of the mean and 2 standard deviations to the right of the mean, right? But when we looked at the table, right, and we looked at, say, 5% on the bottom, let's look for 5%. Here, this is close to 5% here. Was it really 2? I'm sorry, 2.5% on the left and 2.5% on the right. 2.5%, 0.025. Here it is right here. Was it really 2, the z-score for 2.5%, a tail of 2.5%, 2.5% on the left and 2.5% on the right? Was it really that? No, actually it was 1.96, not 2, right? Because that empirical is only an estimate. So really, in this formula, I shouldn't really be using 2, I should be using 1.96. Okay, so let me give you an example that you guys can work out. Okay, I'm going to tell you I took a sample, my sample size is equal to 64, and my mean of my sample is equal to, maybe it's weights, 150 pounds, and the population standard deviation, sigma, is equal to 16, is equal to, let me, 12. I'll call it 12. Sigma is equal to 12. Okay, so give me a 95% confidence interval for this sample. Okay, so remember, what are you going to do? You're going to calculate the standard error, right? You got everything you need for the standard error, right? Sigma and the sample size. And then you're going to calculate a 95% confidence interval. And I'll start you out with the formula. X bar plus or minus the z-score that you need for a 95% confidence interval times the standard error. I'll give you a couple of minutes to do that. That's you guys online too. If you guys online finish ahead of us here, you can go ahead and type it into the chat box if you want what the confidence interval is. Right? Confidence interval is going to be 2 numbers. A lower range and an upper range. How you doing down there? Okay, good. Another 30 seconds. Well, you guys are working on that. Let me see if I can't find something real quick. While you're working on that, let's take a look at this study. This study, in CDC, defined greater British analysis, bivariate analysis. Okay, Mexican American children had a blood lead level of 1.3 micrograms per deciliter. Oh, that's the average they got from their sample. However, that may not be what the actual real population of blood lead levels of Mexican American children is. The confidence interval for the true blood lead level in Mexican American children in this population is 1.2 to 1.4. In other words, their sample came out to be 1.3, but they know, even though they can't tell you how accurately they know that how close they are to the actual blood lead level, but they can tell you that they're 95% sure. They should put 95% in there. They didn't bother to. They're 95% sure that the real blood lead level is between 1.2 and 1.4 micrograms per deciliter. So from now on, whenever you read these abstracts and you see this blood lead level for these children, you know what the confidence interval means, that 1.8 confidence interval of 1.6 to 1.9. You know that means that we got this for our sample, but we're not interested in the sample. The sample is the sample. What we're interested in is what the population of children in this group, what the mean really is for them. And the closest you can get to understanding what the true mean is this idea of a confidence interval. We're 95% sure for the population that it's between these two numbers. Okay, so I'm going to go ahead and do this problem now. And hopefully we'll all get the same thing. Oh, I see a question mark there. Okay, let's see. It's going to be x bar, which is 150 plus or minus z. Now I'm going to do this a little bit more accurately. I'm going to use the actual z value, 1.96, times the standard error. The standard error is going to be equal to square root of sigma over the square root of the sample size, which is 12 divided by the square root of 64, which is 12 divided by 8, which is equal to 1.5. Okay, so standard error is equal to 1.5, 1.96 times 1.5. So rather than round, I'll round at the end, maybe, right? I'm going to round at the end. Okay, so I'm going to take this, clear. I probably mentioned this before. I hate using a computer for a calculator. It's terrible. 1.96 times 1.5. See why I hate it, right? 1.96 times 1.5 is equal to 5.7624. Now, notice I'm going to have to use that twice. I'm going to have to add this to 150, and I'm going to have to subtract it from 160. So I'm going to put it into memory, so I have it available to me. I'll clear it out of there, right? So I'm going to have to use it twice. Okay, so 150 minus that number, which is 1.96 minus 1.5, is equal to 144.23, right? And I'm going to clear that, and 150 plus that number is equal to 155.76. Okay, so I'm not sure where, did I get this wrong? I got different answers.
1.96 by 1.5 is 2.something.
Oh my goodness. You know, I told you I hate using a calculator for doing a computer for doing this. Well, how did I get that wrong? 1.96. You know, I probably didn't clear it out between my botched calculation. 1.96 times 1.5. Yeah, you're right. 2.94. Okay, let me clear my memory and put it into memory. Okay, yeah, I saw your answers. I figured I must have got this wrong. Okay, 150 minus, recall memory, is equal to 147.06. Good. Okay, excellent. You know, probably you could have gotten away with 147 here if you rounded it. right? But why bother? I mean, if you're on a test or something like that, why not just put that number in, right? You're not penalized for not rounding, right? So I'm going to clear that out, and it's going to be 150 plus that value, 2.94. Okay, good. Okay, those are our two numbers. I'm going to copy your numbers here. I'm going to say I rounded it off, called 147 to 153, right? Okay. I'd rather you didn't round it necessarily, but probably I would give you on this kind of problem. I would have given you enough leeway above and below to cover what you would have probably rounded, the amount that you would have rounded this, right? Because it's really 1.47.1 and 1.0, whatever it turns out to be with the next digits. So we're 95% sure it's between these two values. Okay. And we were able to do this because we knew what sigma was, and that we knew that that we were interested in a range that represented two standard errors below the mean we calculated and two standard errors above the mean that we calculated. And that tells me I'm 95% sure that the true mean is between these two numbers. What if I'm not satisfied with 99%? Well, 95%. Let's say I want it to be 99% sure. What should I do now? Plus or minus z times the standard error. How can I be 99% sure? Well, for starters, let me ask you something. If you want to be more certain, if you want to be 99% certain that you have captured the true population mean between your two numbers, do you have to make the interval wider or narrower to be 99% confident? Good luck. Bingo, right? Wider. You got to be wider, because the wider you are, the more confident you are that captured the mean. Well, how are we going to make this wider? How are we going to use a calculation to make this wider? Well, the z-score that we chose before was 1.96 because we were willing to accept an error of 5%. Now we're only willing to accept an error of 1%. So we need to use a different z-score, right? And that z-score is going to represent what standard deviation? It's going to represent 1% error, which means it's 0.0. The error is going to be 0.005, half a percent on the bottom and half a percent on the top. Let's go to our table. Okay, let's see let's look for the areas. Let's look inside these areas and look for 0.005. 0.00, I'm going to use 0.0049. Could be use either one of these two, 510 or 49. And look, what is the z-score that you need to have that small an area at that end, which is 5%? Okay, that's going to be 2.58. So instead of using 1.96, we use 2.58. So X bar is going to be 150 plus or minus 2.58 times my standard error, which is still 1.5, right? So this is going to be a bigger number. So when I add and subtract that from my sample mean, okay, 2.5 times 1.5, up 2.58. I really shouldn't. I want to keep you guys on the right track here. 2.58. Okay. Where'd my calculator go now? Clear. 2.58 times 1.5. I'm going to store this here. Clear it. And 150 minus 3.87 is going to be 146.13. 146.13 and 150 plus, what was it again? 3.58? 153. Yeah, I forget what it was now. 0.87? Okay. Right. And that's going to be my confidence interval. Notice wider than my 95% confidence interval. Well, what about if I only want to be 90% certain? I can make my confidence interval narrower. And in fact, what you would use for your z-score for 10%, possible 10% error, or in other words, 90% confidence, is you would use a z-score of 1.64. So if you remember those three numbers, 1.64 for 90% confidence interval, and 1.96 for a 95% confidence interval, and 2.58 for a 99% confidence interval, pretty much that's all you'll ever have to remember. You'll save yourself a lot of trouble going back to the table and having to figure out what it is. Okay, so those are the three numbers that you should really remember. I didn't mean to obliterate them there. There we go. Okay, so those are the numbers that are important to its confidence interval. Well, I'm going to give you another term. I'm always going to be adding and subtracting the z-score times the standard error. Z-score depends on the level of confidence that we want, and the standard error depends on the population standard deviation and the sample size, right? So I'm always going to be taking this number and adding and subtracting to it, adding and subtracting it to my sample mean. What's a good name for that when you add and subtract something like that? What if I said to you that I weigh 170 pounds plus or minus 30? What's that plus or minus 30? I don't want to. I actually I'm in that range barely. What is that? What is that 30? It's a margin of error. Could be plus or minus. Let's call that the margin of error, right? That's the margin of error. That this number that we're adding and subtracting is termed the margin of error. I don't think it'll come up too much, but that's a good name for it. Oh, good, you got the online. Somebody read the chapter. Good work. Okay, so now, okay, good. So I am going to now. I'm gonna throw another monkey wrench into this whole thing. But before we do that, I want to make sure we understand this. I'm gonna give you one more example. Actually, I think I might have an example here. Let's see if I have one here. Okay. Let's open this, see what we have here. I don't know why it's doing that to me. Those fonts aren't even in the document. And if I download them, it never installs them anyway. So I think it's Microsoft's way of trying to bend my arm into upgrading to a new version. Okay. Okay, so I'm going to take this sample right here. I'm going to take number 2. You randomly sample. Actually, I don't want to take that. I don't want to take that one right now. I'm going to go back to a made-up sample first. The mean of population is known to be. Okay, let's take this second one. A random sample. I'm going to blow it up a little bit so we can read easier. Second one. A random sample of size 36 has a mean X bar equals 165. Assume the population is normally distributed with a standard deviation of 18. Calculate the standard error for samples of size 36. What do you need to know about that in order to calculate the standard error? You need to know the sigma for the population, well, that we've been given that. And you need to know the sample size, right? So it's going to be 18 over the square root of 36. So what do we get for a standard error? Okay, we get 3. Standard error is equal to 3. Compute a 95% confidence interval for the population mean. Okay, what do we need to know there? We need to know the mean X bar, mean of our sample X bar, plus or minus the z-score that we need to use for 95%. We know that's 1.96 times the standard error for our samples of size 36, which we know is equal to 3. Okay, so let's calculate that. You guys do it, and when you're done, we'll do it together. Okay, 36. Next bar again. 165. sigma for the population was equal to 18, I think, right? 18. So standard error, sigma over the sample size is equal to 18, and then square root of 36, is equal to 18 over 6, is equal to 3. So 95% confidence in XY plus or minus 1.96 times our standard error for these sample means. I mean, what's that going to be equal to? It's going to be equal to 165 plus or minus 1.96 times 3. And I'll leave this and figure that out. Okay, I'm going to go ahead and work on this with you guys now. So let's see, I'm going to clear out this stuff here. It's going to be 1.96 times 3 is equal to 5.88. I'm going to put that into memory. Clear this, and it's going to be 165 minus that margin of error, which is 159.12. 159.12. And the upper boundary is going to be clear and be 165 plus 5.88, which is going to be 170.88. Okay, we have agreement this time. I got it right for a change. Okay, so that's our 95% confidence interval. Well, now I'm going to ask you to calculate a 99% confidence interval and a 90% confidence interval. Okay, and I'll leave it for you guys to figure out what to do. I'm going to give you about 2 minutes on this, and I'll give you 2 minutes, and then we'll do 99, and then I'll give you another 2 minutes. We'll do 90. Okay, I'm going to go ahead and solve this now. Okay, so let's see, what are we going to do now? Well, the difference here to get the 99% confidence interval, it changes the z-score that we're going to use. Instead of using 1.96, we're going to use 2.58 times our standard error. That hasn't changed. That's still 3. So it's 165 plus or minus 2.58 times 3, which is equal to here 2.58 times 3 is equal to 7.74. Okay, remember this is called now our margin of error. And I'm going to add and subtract that from our sample mean, 165 minus, okay, where was I here? 2.58 times 3. Okay, memory plus 165 minus memory is equal to 157.26. Good. Okay, and I see somebody else calculated the upper limit, which turns out to be 172.74. Excellent. Good. I think you guys are starting to get this, right? Okay, and now finally just finish up with our 90% confidence interval. Okay, so you guys give 90% confidence interval a shot. And this is pretty much if I've given you this data, this information, including the population standard deviation, this is what you need for numerical variables to calculate what the confidence interval is for your sample, for your population mean rather, from your sample. And I'm gonna work in the background here so we don't kill too much time. So it's gonna be, what is it gonna be? 1.64 times 3. Okay, let me clear memory, add this to memory. Clear that. And it's going to be 165 minus 4.92, which is going to be 160.08, and 4.92, 4.9, was it 4.92? 4.98? Oh no, 4.92. Added to that would be 169.92. There we go. Good. You guys you're actually doing it ahead of me now. That's great. Okay, so let's take a break for about 10 minutes. And we'll come back and we're going to take the next step. Okay, but I think you guys are starting to get this, right? Makes sense. Okay, let's take a break. You guys online too. I'm going to pause the recording. Make sure
this and we got our screen going again. Recorded.
Okay, you guys online, just let me know that you can see and hear me again. Okay. Okay. Okay, so let's get back to this. So let's take a look at this. Let's say I were to tell you, actually I'll use an example. You know, let's see, population mean. I don't have one here. Where was that other document that I had? See if I still got it open. Okay, I'm going to take this first problem. Okay, suppose we want to know the true population proportion of Irish Americans who approve of a wider representation of all groups. This was a big issue in New York 15 years ago. The St. Patrick's Day parade, they would not allow gay groups to march in the parade as a group. Became a big issue. There was a lot of debate about it, and so on and so forth. It's a privately held parade, although the city provides, security and kind of stuff. So it was really became a big issue. So in 2000, let's say we go back 20 years, say roughly 20 years, and we want to survey people that are actually in the parade, to take part in the parade, see how they feel about a wider representation of all groups in the parade. Okay, so these numbers are fake, right? They don't really represent a real survey. But let's say you randomly sample 1,381 people in the parade, whatever way that you organize this sample. And now, of course, there's 100,000 people, or more than 100,000 people that take part in the parade or watch the parade, right? Probably might be 500,000 people that actually watch the parade. So this sample of 1,381, it's a big sample. but it's still a small percentage of the people that actually represent this population. So 1,381 respondents, 496 says that they're in favor of a wider representation. So we have our sample size is 1,300 and what did I say, 96? And our number of people that said yes was, where'd it go? 1,381 and 496. 1,381 and 496. 1,381 and 496. Okay, so what proportion of the people that you surveyed told you that they would favor wider representation? Well, 496 out of 1,381 people that you sampled. Well, what proportion is that? Okay, let's calculate that. 496 divided by 1,381. And that proportion is 0.359, almost 36%, 0.359. Okay, about a little less than 36% favored wider representation. Okay, so now, this P here, usually I use P to represent the entire population. Kind of like I use mu and sigma to represent the standard deviation of a numerical variable. Now, when I'm talking about a binomial variable, yes and no answers, right? That's binomial. The value for answer, favor or not, is a yes or a no. So it's only two values, like flipping a coin, right? So the proportion of the entire population, I usually use P. But just like for when I take a sample, I use X bar and SD for standard deviation and mean. Okay, I'm going to use something different for this to indicate that it's from a sample. I'm going to say P, but I'm going to put a cap on top of it, kind of like I put a dash on top of it or a bar on top of the X. So P cap is equal to 0.359. Now, what is the actual population proportion? Just like the mean of the population, I'm never going to know that unless I sample everybody in that population, right? So all I'm ever going to know is P cap from my sample. But I really want to understand how well I know or how well I can predict what the real population proportion is, so that so that I have a better idea what's going on in this population, right? Because this really doesn't help me much if I don't know how close I am to the true population proportion. Okay, so we're going to do the same thing. In order to solve this, we're going to say P cap plus or minus 1.96 for a 95% confidence interval. And I'm going to multiply that times the standard error. The standard error of repeated samples of size 1,381 from this population. Okay, now, do I know what that's going to be, that standard deviation for this population? Do I know what it is? No, I'm never going to know it. But you want to know something. When you take a proportion, you almost always take a sample size that's so large that we don't really worry about the standard deviation of repeated samples anymore. We just say that we can calculate it this way. We're going to calculate the standard error by saying the square root of P, I'm going to say P for now, P times 1 minus P, right, over N. Okay, this is the square root of this whole thing, right? So notice I said P, population proportion, because, just like knowing sigma, I really want to know sigma to make this valid. But since I don't know sigma, and this is almost always a very large sample, I'm going to use P cap instead of, I'm going to go ahead and justify using P cap instead of P. So this is equal to the square root of 0.359 times 1 minus 0.359, which is 0.644. Okay, tell me if I'm wrong, over the sample size, which is 1,381. Okay, what does that mean that the standard error is equal to? Okay, I'm waiting for you guys online to make sure that I'm right, right? Did I get that right? I'm going to move forward on this so that, okay, good, thanks. Okay, let me clear this. Okay, so let's figure this out. 0.356 times 0.644 equals this. Divide that by 1381. Comes out to this. Looks a very small number, right? But you know, when we take the square root, it's going to make it a bigger number. Just like multiplying 0.01 times 0.01 gives you 0.0001, smaller number. Finding the square root of it gives you actually a bigger number. Okay, so it's going to be 0.013. I'm going to call it 0.013. Now, I've been telling you not to, I'm doing this because I need to get through this quickly, but I might have said 0.0129, you know, just to make sure I have an extra significant digit or two. So this standard error is going to be 0.01288. 0.128, I'm going to call it 9. So now I'm going to use this in my confidence interval equation. So my sample proportion was 0.359 plus or minus 1.96 times my standard error, which is 0.0129. Okay, what's my margin of error here? Okay, let's go back here. I'm going to clear this, and I'm going to say 1.96 times 0.0129. So my margin of error is 2.5%. 0.025 is 2.5%. So I'm going to store that. Okay, I'm going to clear it off. I'm going to say 0.355 minus, recall that, going to be 0.329, 0.330 really. 0.330. Okay, and clear. And I'm going to say 0.355 plus, recall memory, 0.380. Right? So it's going to be between, or 95% sure, the true confidence interval, and you guys will tell me if I made a math error there, right? I'm counting on you. The true 95% confidence interval tells us that we're 95% sure that the true proportion is between 0.33%, 0.330, and 0.380, between those two. So we can use the same idea about the nature of samples and the way that they're distributed. In other words, that central limit theorem we were talking about a couple of weeks ago, right? That central limit theorem, we can use that for proportions just as we use it for numerical means. There is one other good thing about the central limit theorem. You guys remember that by any chance? What was the other thing that's really handy about the central limit theorem? Exactly. That's really important. What's really important here is that the central limit theorem, let's say you have a distribution which is not normal, which is skewed or it has bimodal or something like that. Let's say it's a nasty distribution, right? Let's say your original distribution is kind of weird, right? It's not really normally distributed, and the mean is over here somewhere, right, of your population and so on and so forth. Well, if you take samples from this population, because the mean is here, half the time you're going to get people here, half the time you get people here. So when you actually average those results, X bar 1, X bar 2, repeatedly taking those samples, if you only take a few of them and you plot that, well then, you're still going to get kind of a funky distribution. But if you take many, say an infinite number of samples from this population, the result will be a normal distribution. So even though the population is not normally distributed, you can use the central limit. You can use the central limit to calculate a confidence interval as if with the assumption that your sample distribution will be normally distributed. The real key here is that if you have a small sample size equals 6, you can't depend on this too much. because it doesn't really have a chance to really even out your sample distribution. If your sample size is larger, then you can make up for more and more inconsistencies in your population distribution. But the real takeaway here is that this works even if the population distribution isn't perfectly normal. Okay, so that gives us a lot of flexibility.
I just want to clarify.
Sure.
For the central limit theorem, it's good to use it if it's a sample of the population or both.
You can use the central limit theorem tells you that if you take repeated samples from that population, right? Sample it again, sample it again, sample it again. If the sample size gets as the sample size that you're taking, if you're taking sample size 6 and you take it once, twice, 100 times, and then you draw a new distribution based on that sample size of 6, well, it kind of starts to turn into a normal distribution, but maybe because the small sample size, not quite there. But if you take a large sample size, 100, and you do it once, twice, 3, 100 times, 1,000 times, and you then draw that distribution, it's going to be very normal. It's going to be normally distributed. Normally distributed sample distribution is what you use to justify that confidence interval, the calculation of that margin of error for calculating your confidence interval. So the real takeaway here is that what we're doing here in calculating confidence intervals does not require that you have a normally distributed population to begin with. You can get away with not having a normally distributed population, particularly if the sample size of your sample is large. Sample size of your sample is small, things get a bit dicier than this. Okay, and I'm about to bring up where they become dicey. Okay, so now let's take a look at where we're going with all this. Okay, where are we going with all this? I'm thinking for a second here. I know where I'm going with all this. Okay, now let's say real life now. We're talking about pie in the sky. We know the population standard deviation, so on and so forth. Let's talk pie in the sky now. Let's forget the pie in the sky stuff that we know, stuff about the population that we really almost never know. For instance, mu, unknown. We have no idea. Sigma, unknown. We don't know what that is, and we're never going to know what they are, right? So how are we going to predict what they are? Okay, so now if we take a sample, I'm going to take a sample of size 100. And I take that sample, I select 100 people from the population randomly, and I find the mean. X bar turns out to be, let's say, turns out to be 90. And, what about sigma? I need to calculate a standard error if I want to calculate a confidence interval. But in order to do that, I need to know sigma over the square root of the sample size. I know the sample size because I'm taking the sample, so I know what the sample size is. Well, what am I going to use for sigma? Well, if I take a random sample from a population, right, randomly sample 100 people, those 100 people, when I take the average, the average is going to approximate the mean. I don't know how well at this point, but it's going to approximate it. Well, the variability, if I take 100 people, the variability of those 100 people is going to be roughly the same as the variability of the population. So the standard deviation for my sample, not my sample means, but the standard deviation of my sample is going to approximate sigma. It's going to be approximately sigma. But you want to know something? Before, when I told you what sigma was, we knew this thing exactly. We know what sigma was exactly. What I've done now is by saying that we don't know sigma, and you're forced to use the sample standard deviation. I'm going to say that it's equal to 10. And you're forced to use the sample standard deviation instead of sigma. Well, now, there's two things we don't know now. We don't know the mean for certain, and we don't know the standard deviation of the population for certain. So now we've introduced extra uncertainty, right? So I can use, if I can get the page back, wrong direction. I can use the standard deviation of the sample to represent sigma. So I can say it's equal to, instead of that, we're going to say standard deviation over the square root of 100. That's equal to 10 over 10 is equal to 1. I can use the standard deviation, but now I don't know that they're really equal. I know they're probably close, but I don't know that they're really equal. So if I knew sigma and I calculated my confidence interval was between 80 and 110 was my 95% confidence interval. And I knew what sigma was. Sigma was equal to 10, right? I knew that that was the case, right? In this case, I don't know that it's really equal to 10, but let's say I knew it was equal to 10. I calculated my confidence interval using sigma over square root n, and I found that it was equal to 80 to 110, my interval. So now, if I say I don't know this, and I've introduced more uncertainty, what do I need to do to this range in order to make sure that I'm still at 95% confidence? What do I need to do to make up for more uncertainty? I need to make it wider, right? If I make this wider than it would have been if I knew what sigma was, it allows me that extra little bit of insurance to make sure that I'm really 95% sure that true mean is between these two, right? And how much should I add now for that level of uncertainty? Well, you want to know what's going to affect how uncertain we are, how close we are to, how close sigma, how close the standard deviation really approximates sigma. What's going to determine that? What's going to determine that is going to be the sample size. So the bigger the sample size, the smaller the adjustment we have to make. The smaller the sample size, say n is equal to 10, the bigger the adjustment, because we're guessing at the standard deviation of the population, sigma. We're guessing at it from only 10 people, right? So we're more uncertain. So in order to make that up, we have to make our margin of error wider. Well, how do we do that? The way that we're going to do that is we're going to use another table, which adjusts the z-score for the uncertainty that we have that's caused by not knowing what sigma is. Okay, let's look at that table. I'm going to find that table here. It's on Blackboard, but I'm going to look for it here. Oh, got the wrong one. Okay, here, that's the one. That's the one I just opened? No. Here we go. There's the T table, right? How do we use this table? Well, notice that there are columns here. 80%, 90%, 95%, 95% confidence interval. That's what we're interested in, isn't it? So the 95% confidence interval, 99, 98, 99, 90, 98 and a half. Usually we're just interested in 90, 95, and 99. Most often just 95%. So let's go down here. And we notice that the values that are here are what we're going to use as the z-score instead of our z-scores. These are called t-scores, right? Still number standard deviations, they're called t-scores. So if we have a sample of size 10, instead of using 1.96, we're going to use 2.228. If we have a sample of size 5, we're going to use 2.57. Notice the numbers get bigger. The higher the uncertainty is, small sample is higher the uncertainty is, the bigger we have to make up for it. The 1 degree of freedom, 12.7. Oh my goodness, wow, that got really big. What does degrees of freedom mean, right? Well, we can't really guess if I just give you if I take one person, if I am interested in the average weight of students in this building, and I pick one person, and they happen to weigh 145 pounds, what do I know about the variability of the weights? Zippo, nothing, right? Because I only know one person. I don't know how variable it is. So you need more than one person. So the minute you need more than one person to determine variability, we say, okay, one person doesn't count. So you need at least two people even to start to think about variability, right? So we're going to call 2 people 1 degree of freedom, right? We're going to call 3 people 2 degrees of freedom. So the number of degrees of freedom is the sample size minus 1. So if I wanted to use a sample size of 10, I would look for 9 degrees of freedom, and I would use this number to calculate my confidence interval. If I had a sample size of 25, I would use this number. If I had a sample size of 30, I would, what do you notice about these numbers as the sample size goes up? What do they get closer and closer to? 2.0, 60, sample size 60, 2.0, sample size of 80, 1.99, sample size of 100, 1.984. How about a gigantic sample size? They call it infinity, but how about a super big sample size? It becomes the same as a z-score. In fact, a lot of instructors, a lot of people, a lot of books will say, you know, the sample size is large. Say a sample size of 100. You would go to this table and say 100, I'm going to use 1.98. You know, sample size of 100, I'm not even going to bother. I'm just going to call it 1.96. So a lot of times, if you're working with a large sample size, rather than use the t-table, you're not going to bother. You're just going to substitute 1.96 and ignore the fact that you don't know the population standard deviation. But small sample sizes, it's really important that you use the t-table. So what if you wanted to be 99% certain? Well, in that case, you would use this column, right? Notice it says the right tail probability, 2.5 for this, says you can't really see that, 2.5% for 95% confidence. That means the right tail is 2.5%, the left tail is 2.5%, just like we were looking at it before. And for 99%, 0.5% chance for error on either tail, right? So that's a 99% confidence interval. This table is that some tables won't show you that. They'll just show you this. And you have to figure out that represents 95% confidence. This represents 99% confidence. This table's nice. It gives you those values, right? So let's apply this. Okay, so let's say we have this situation right here, except, you know, I'm going to change one thing here. I'm going to make my sample size 25. I'm going to use the sample size of 25. X bar is 90. My standard deviation for my sample is 10. I don't know sigma, so I have to use 10 to calculate my standard error. The square root of 25 is 5. So my standard error is equal to 2. So what's my confidence interval now? It's going to be X bar plus or minus. Now, I'm going to write here, instead of writing Z, I'm going to write a t value times my standard error, right? I'm going to write the t value for a 5% chance of error. In other words, 95%, right? So my t score, substitute here for my Z score. Why did I put t? Because I don't know sigma, right? And my sample size is small, right? So if I knew sigma, I would have used Z, which would be 1.96 automatically. But since I don't know sigma, I have to use the t value instead of the Z value. And that t value is not going to be one number like 1.96. The number is going to be dependent on the sample size. Okay, well, let's give this a try. So it's going to be 90 plus or minus the t-score for a sample of size 25. Oops, wrong one. Here we go. Here's our table. So 95% confidence interval, 24 degrees of freedom, right? Because sample size is 25, 24 degrees of freedom. I go over to the middle, 95% confidence interval. It's going to be 2.064. So this is going to be plus or minus 2.064 times my standard error, which was 2. So it's 90 plus or minus 4.128. Yeah, 120, 4.128. So that's going to be 94.128. And subtract 4 from that is going to be 95.278, I think. Right? Lay these together, so hopefully they'll work. Yes, I think they do. Okay, so that's going to be our confidence interval. Had we known what sigma was, or if sigma, if our sample size were, let's say our sample size was 500, right? Really big sample size, I would have just simply used 1.96 there. And is this confidence interval, is it wider or narrower than if I had used 1.96? The wider or narrower? It's going to be wider, right? Because I used a bigger number to calculate when I add and subtract my margin of error. So it's going to be wider, which makes up for the uncertainty that I had when because I didn't know what the population standard deviation is. And I had to depend on the sample standard deviation as an estimate for the population standard deviation, that extra bit of uncertainty. This makes up for it. But now I can have a valid confidence interval for this sample. Okay, I'm going to give you guys one more to do yourselves. And I'm going to give you one more to do yourselves, and I'm going to call it a day. If you go over here to Blackboard, there's a video lecture section. I'm going to leave that up to you guys to watch on your own, rather than just play it here and stare at it. Okay, let me just make sure it's there. Confidence intervals. 7 in class. Yeah, these are videos from the previous semester. You can look at those. I'll be uploading today's videos. These are in the lab section, right? In class exercises. I gave you some older videos also if you want to look at it again from a different, maybe I did it differently the last time. Maybe I was a little younger and I made fewer math errors. Who knows, right? So let me go back. Let me go back one step here. And I think if you go into the lecture portion here, you'll have a recorded lecture from Levi, also broken up into sections, right? A recorded section from Levi, which discussed this idea of p-values. Now, it does go a little bit further because it starts to talk about something called the t-test. We're not up to that yet. So you can watch that if you want. Don't worry, just go up if you want, just go up to what we did here today. And that will be enough. If you want, you can look ahead in these videos for a little bit and maybe get a feel for some of that stuff as well. Okay, to kind of get a preview of it. That's what we're going to do next time. We're going to do t-tests. And the t-test is just a way of comparing more than one mean to each other. So let's say, for instance, we knew that the average total cholesterol, let's say that we suspected that the average total cholesterol for Americans is more than for Frenchmen. So we want to see if we can prove that. We say to ourselves, you know what we're going to do? We're going to take a sample of 1,000 Frenchmen, find their total cholesterol, find the average total cholesterol. And then we're going to take Americans, 100 Americans, not 1,000, 100, we're going to find their total cholesterol for each of those samples. Do we know what the total cholesterol is for all Frenchmen? No, because we can only take a sample. For Americans, no, because we only have a sample. Now, can we say with 95% certainty that the true average, the true population, average population total cholesterol for Frenchmen and Americans are different? Do we have enough evidence to say that they're really different? We're going to take our confidence interval, turn it around again. The idea is confidence interval and this t-value, we're going to turn it around again, and we're going to use it to compare means of two groups. It's going to be the same basis, but we're going to spin it around again so that we can reuse it in a way that's convenient for solving those kind of problems. You don't have to worry about that for this week. We'll get on to that next week, and trust me, it's not as hard as it sounds. It's going to be pretty simple. Okay, so I want to give you one more problem. Okay, a major metropolitan newspaper surveyed took a simple random sample of 200 voters. They asked whether they plan to vote on a new bond act. 110 of those surveyed said that they plan to vote yes. What's the 95% confidence interval of voters in this population who will vote yes? Okay, so let's look up the 95% confidence interval. And what's the margin of error? You're going to do that on the way to getting this, right? This is for a proportion again. Okay, so my sample size is equal to 200, and the yeses equal 110. So my P cap is 110 over 200, or 0.55. So tell me, what is our confidence interval, 95% confidence interval, for the true value of P, right? For the true proportion for the entire population. Okay. And how did we figure that again? We said P cap. Well, first, if we were working with numerical variables, it would have been X bar plus or minus either T or Z, depending on whether we knew sigma and how big the sample was, times the standard error. We'd choose which one of those two to use. Or we could do P cap plus or minus. You want to know something? As I mentioned before, when you do proportions, you're generally dealing with sample sizes that are large. So we don't bother with the t-value there. We only use z. We make believe we know what the standard deviation is. We only use z there, right? So if we're numerical, we would have to decide whether you use t or z, and then substitute the right value based on the sample size. Okay. With proportions, we don't worry about that. In this case, the sample size is 200. The other rule that we use is that both sides of the results have to be greater than 15, right? So in other words, I couldn't have a sample n equals 200 and the yeses equal 10. That doesn't work, right? Because the yeses are 10, the no's are 190. One side is less than 15. We broke that rule, that assumption, right? And the other side doesn't work either. We can't say that the yes is 190, making the no's 10, right? So that it's 0.95, right? But the no's are too small, so I can't use that. I can't use that there either. But in most cases, these are both bigger than 15, and the total sample size is large. So we can go ahead and use the z-score, right? Tons of standard error. Okay, so I'm going to start to fill this in. 0.55 plus or minus, I can use 1.96 here, times the standard error. Well, how do I calculate standard error for proportions again? Square root of p times 1 minus p over n. Let's see what that is. 0.55 times 0.45 over 200. Clear? Okay, so it's going to be 0.55 times 0.45 equals this, divided by 200 equals this. Okay, and find the square root of that. Where'd it go? Here it is. It's about 3, that looks like 3.5%, right? So that equals 0.035 equals 0.035, right? So this is going to be 1.96 times 0.035, right? Okay, so if I multiply, I'm going to use 2 here. Do as I say, not as I do, right? So I'm going to round that to 2 just to speed things up. But you should actually calculate it out. 0.55 plus 2 times that is going to be 0.07, right? So the margin of error is 7%, 0.07. So my confidence interval, my 95% confidence interval for the true P is 0.48 to 0.62, 48% to 62%. I'm 95%, the true proportion of people in this population that are going to vote yes is between 48% and not 62%. Am I 95% sure that this proposition is going to pass? No, I'm not, right? Because it could be less than 50% are going to vote yes, right? So I can't say it's different than 50%. Had my confidence interval been 0.52 to 0.60, I could say with 95% certainty that the population with population proportion of people who are going to vote yes is greater than 52% and less than 60%. I could say I'm 95% sure that this is going to pass. But since that value 50% is inside of my confidence interval, I can't say 50%. I can't say with 95% certainty that it's not 50% or 49%, in which case the proposition would fail. So where do you see this all the time? You see this in polls, right? You see it all the time, right? You see all the time, you see that instead of expressing it as a confidence interval, they'll say right now the Democratic Party is leading by 55% with a margin error of plus or minus 7%. You see it expressed that way in a poll, but it really is the same thing. They do exactly the same thing when they're polling. Okay? So next time you see a poll, right? Next time you see a poll and it says the proportion of people that are voting for this guy is this guy's got 30% of the vote, plus or minus 3%, and they give you so you need to know the sample size, right? And they give you the sample size, right? Figure out what the margin of error is, what the confidence interval is, right? And figure out, see if you get the same, if they give you the sample size. They may not give you the sample size. If they give you the sample size, figure out what your confidence interval would be and see if it really comes out to be 27 to 33. My guess is it's not. And you know why it's not? Because they do a special cheat. Instead of using the square root of 0.3 times 0.7 over the sample size, right, whatever it is, say 1,000 people, they use the square root of 0.5 times 0.5 over the sample size. Why do they use 0.5 times 0.5, do you think? That'll give you the biggest margin of error, right? 0.7 times 0.3 is 0.21. 0.5 times 0.5 is 0.25, right? So they do that. It's kind of a safety thing, right? That turns out to be the biggest number. And that's really what they use for their confidence interval, for their margin of error. It also does one other good thing for them. If they sample 2,000 people and there are 3 candidates, and this guy gets 30% of the vote, and this guy looks like he's going to get 12%, and this guy looks like he's going to get 48%, right? If you did it individually with confidence interval and you did it using the real calculation for margin of error, you'd wind up with this guy being plus or minus 3%, and this guy being plus or minus 4%, this guy being plus, because the proportions are different. So by using 0.5 times 0.5 over the total sample size, you can say all of them are plus or minus 3%, the same percentage, which is really the worst case scenario for any one of them, right? So they don't have to explain to their readership why there are different percentages of certainty in the same poll for different people, which is really true, because there really is, because the guy that's got the least, the guy that's got 12%, that's the greatest variability in terms of the standard error, or the smallest variability. The guy that's closest to 50% is where the biggest variability is, right? So you got a way of expressing it that laymen will understand and not question why is the margin of error for this guy different than the margin of error for that guy, and you sample the same number of people, or it's the same people within this group that you sample. Okay, so it gets more interesting from here on out because we're doing real statistics now. This is stuff you're going to see in polls, you're going to see in articles, in abstracts, confidence intervals, and so on and so forth. And as we go forward, you're going to see even more of this stuff. Okay, so hopefully for you guys online, please also watch those videos, that lecture video, at least the first couple. You can once you start talking about the t-distribution, it's up to you if you want to wait till next week or you want to go ahead and get a little bit of a jump on it. But give that a try as well.